At the heart of the flight simulator is a mathematical model of the Earth's surface, which is created at the National Image and Mapping Agency. Satellites and aircraft passing overhead record images of the Earth below. These images overlap and are linked together by common points to form a large seamless picture. The geographic location of the picture is determined by the lens size in the camera and the location of the satellite, measured by tracking stations on the ground. As the camera passes overhead, it photographs each location from two angles. By comparing the difference in perspective, computers can determine the elevation of the land at 100-meter intervals or posts. Using this technique, the agency has collected elevation data for 90% of the Earth's land surface.
The terrain data is the math model that gives us the hills and the valleys. It's a mathematical representation of the Earth, which allows us to do several things, a couple of which are to locate ourselves precisely on the Earth, overlay imagery, tie it down precisely, put our intelligence information, our operational information, our planning information, and get that to the people who have to have it. Everything ultimately is tied to the Earth. The mathematics is transparent to the user, but is, the basis for everything that we do.
In 1995, the flight simulator was put to the test. Vic Kuchar and the support team helped NATO pilots plan airstrikes against targets in Bosnia. 2 months later, peace talks began. Kuchar helped the negotiating team to create a new role for this technology.
All of these people on a 24-hour-a-day basis would come to us, and we would fly them, virtually speaking, to Bosnia. They had to have confidence that this mathematical model was ground truth.
Attention focused on the city of Gorazda, which was claimed by the Bosnian faction. To establish peace, it was critical to link this isolated pocket to the Bosnian homeland.
In order to connect these two, we had to find some agreed-upon corridor. So we physically, on a map, laid down yardsticks and said, here's our corridor, what do we have in there? Anything that you can gain inside of your line will add to your total wherewithal. A stream or a power line. Now here's an example right here. This valley belongs to the Serbs. And you can see how we had to deliberately pull this thing at 90 degrees out and away from this valley. So there was some strong negotiating there, you can bet on that. The one leader asked me to fly him to this one little town. And as we were going down through a valley and there was a little stream crossing there, he said, can you hold here? Which I did. I stopped the machine. And he said, see this bridge? I used to swim off of this as a boy. Seeing that reinforced, I believe, in his mind that this data was real.
After 4 days, the corridor boundaries were established, and the warring factions reached a settlement for peace.
There was a lot of tugging and stretching of that rubber band line between the two entities. But the terrain visualization equipment, our math model, and data allowed us to fabricate this corridor, unlike anything ever done in history as far as I know.
The mathematics that was harnessed for peace is the product of thousands of years of measuring the Earth.
Geometry means measuring the Earth. It's a Greek word. The Greeks were the first to realize the Earth is not flat. It takes the form of a sphere. For us, it's such a commonplace, it's hard to realize what a leap that was. And to picture the Earth as this gigantic ball floating out in space and people on the opposite side hanging upside down by their heels, that was very, very hard to conceptualize. The Greeks had this mystical idea about circles. They noticed that if you look at the path of stars during the course of a night, they'll form a circle. And then, of course, the moon is a perfect circle, as is the sun. Circles and spheres, both, seem to be a very essential part of the way the universe was constructed. When the Greeks were noticing that as you moved further north, the North Star seemed to be higher and the sun would look lower in the sky and the reverse in the south, they at some point realized that the reason for that must be that the Earth is spherical and not flat. By getting this geometric framework, they were able to really understand the reasons for what they observed. Long before we went to the moon, you could draw an exact map of what the Earth was going to look like when you got out there. Maps have become one of the central notions of mathematics. They started out with a very concrete problem of taking a portion of the Earth's surface and then drawing a picture of it on the plane where you have an overview of it. You have two different domains and you're transferring the information from one to another. And that notion is now called a map.
With the mathematical tools, the Earth has been surveyed in greater and greater detail. But not long ago, many places were still unmapped territories.
In the early 1930s, there was an awful lot of North America that was still just plain blank on the map. And there was an area there of around 5,000 square miles between the Yukon Territory and Canada. And all it said, very neatly in it, I'll never forget it, in little lines, high mountains 10 to 12,000 feet high. And nothing but that in blank white paper. So we told the National Geographic if they wanted to finance an expedition into the area that we would go in there and find out what's there.
For thousands of years, explorers like Brad Washburn mapped the Earth by standing on its surface. But in Yukon Territory in 1937, Washburn helped map-making take a giant leap.
This was my first really